Intro to Calc. Hope you guys are having a great day. We are starting chapter 2. So we already kind of started to talk about the difference between velocity and speed in class. And so this is a continuation on that, assuming that you already know that velocity is basically speed but with a direction. So you can have a positive and negative velocity, but you can't have a positive and negative speed. So what we're going to look at today is how do you find the average velocity of a particle, given a function, and then how do you find the instantaneous velocity, which is basically like what is the velocity like in this instant, like right now, not like on average over time, but like right now. And so real quick, I don't think I've done this yet, but SWABAT basically all it stands for is students will be able to, and then kind of like these are our objectives of the day. So hopefully by the end of this video, the end of this lesson, you should be able to use limits to determine the instantaneous velocity of a particle and connect the slope of a curve to the velocity. And so that's what we're going to talk about today. So first things first, we're going to talk about instantaneous velocity. So say for example, like you throw a ball in the air, right? At some point, right, the velocity is going to be really fast, and then at another point, like when it reaches the top and then comes back down, right at the top moment, as it's turning around, the velocity is 0 in that moment. And so over time, the velocity of the ball is changing, as is its direction, right? So like if you're throwing it up, you should have a positive velocity, and then as you come down, you should have a negative velocity. So it goes from a positive velocity to a 0 velocity, and then down to a negative velocity. So in order to describe the instantaneous velocity, we need to first kind of refresh the average velocity. So we're going to look at this graph first. Okay, so recall from class that your average velocity is your change in position over your change in time. And like to relate this back to like that formula you know about distance equals rate times time, right? This is true if you're going at a constant speed, but sometimes your speed is changing. So we can get the average velocity by looking at like how far you've traveled over how much time you spent traveling that distance. And you know, this is related to distance equals rate times time. If I divide both sides by t, I get d over t equals the rate. And in this case, we're talking about velocity is our rate, and that's our distance divided by time, right? So it makes sense. It makes sense with physics, makes sense with mathematically. Visually on the graph, like let's say I wanted to find the average velocity at time equals 1. So here, like, okay, what's the speed when 1 second has gone by, right? That would be the speed right here. But the problem is, like, we don't really know how to calculate the speed at a single instant, right? So we have to kind of, at this point, we have to kind of look at the average speed. So you might take the speed at maybe 0.5 seconds and the speed at 1.5 seconds, or sorry, you look at the position at 0.5 seconds and the position at 1.5 seconds, you find the difference between those positions, find the difference between time, and you find the average velocity. So if you take a look at around 0.5 seconds, so I could actually find the actual position by plugging it into the function, but for now I just want the visual, so we're just going to do an approximate. So if I plug in 0.5 for my time, so after 0.5 seconds, half a second, my ball is 6 units, whatever our units are, feet, meters, inches, whatever it is, high, right? This is my position at 0.5 seconds. So at t equals 0.5 seconds, my height is 6, which is just a point, right? 0.5 comma 6. And then I'm looking at my height at 1.5 seconds, and that is just my height is 0 after 1.5 seconds. So if I want to find my average velocity, I take the change in position. So I have gone from 6 down to 0, so that's a change of -6 units in height. And I've gone from 0.5 seconds to 1.5 seconds, so that's a change in 1 second in terms of my time that has passed. So remember, with velocity, the positives and negatives really matter, right? The direction that you're going matters. So in this case, you need to make sure you have your second position minus your first position and your second time minus your first time. So in this case, right, that's -6. Let's just assume we're in inches and seconds for the time being. You have a decrease in 6 inches for every 1 second. So that's your average velocity for that time. So another way to look at this, right, is this is the same thing as finding like the average slope between the 2 points, right? This is y2 minus y1 over x2 minus x1. This is actually like the slope of the line that's connecting those 2 points. So the thing is, if I want to know my instantaneous velocity, right, I need to get closer to this point, right? 0.5 seconds and 1.5 seconds are pretty far away in terms of their height, away from 1 second. And so what I can do is I can actually bring this point closer and maybe do like 0.9 seconds, and on this side do 1.1 seconds. So in this case, right, if I move my time closer to the time I'm interested in, I get a better estimation for the velocity at that moment. So here I'm going to, again, this is an estimate, right? So say this is approximately 0.9 seconds, and my height is approximately 5.5. And then here my time is 1.1, and my height is approximately 3.9. So in this case, right, my average velocity is my change in position, 3.9 minus 5.5, over the change in time, which is 1.1 minus 0.9, and that is equal to about -8 inches per second, right? Remember, I assumed my units to be inches and seconds because I didn't give them to you in the problem. And basically what that does is it allows us to get even closer to the instantaneous velocity. And again, that is the same thing as the slope of the line between those 2 points. Remember, it's rise over run, so you would do the same thing, right? How much am I going up? And in this case, I'm actually going down, so -1.6, and I'm going over 0.2. So average velocity and the slope connecting those 2 points are the same thing. So the idea is with instantaneous velocity, I'm actually bringing these points closer and closer to the point I'm actually interested in. So the next one, maybe I do 0.999 and 1.0001, right, on either side, and I will get closer and closer to that average velocity. And what I'm doing actually is I'm making that width on the x-axis as close to 0 as possible without making it 0, right? Because if I'm actually going over 0 on the x-axis, then I would be dividing by 0, and that's bad. So this should be starting to ring some bells that this is like kind of related to something we just did in the last chapter, right? I'm getting closer and closer and closer and closer and closer to 0, but I'm not actually equaling it. So what I'm going to do is I'm going to actually look at the difference between T1, the time I'm interested in looking at, and a time that's like a small distance away from it. So like in this case, right, T is 1 here, and that's what I'm interested in. And I'm going to go over a very, very small amount. Let's call it h. And so in this case, right, I have gone over h from 1, which means that this new t value is 1 plus h. And I'm interested in looking at what is the slope, or the change in y over change in x, between those 2 points. And that's how we come up with the formula for the instantaneous velocity at a point. And that's also the same thing as the instantaneous slope of a curve at a point. Okay, so this is how we get our formula. And I'm going to kind of like talk you through this for a second here. So we have s of t, which is like the same thing as using f of x, right? S is position, it's a function of time. We're used to using f of x, right? f is the function or the y value, and x is the x variable. And in this case, we're just going to use s and t. Then you have the instantaneous velocity at t equals a. So like in our case, right, t equals 1. And that is equal to the change in y. So this is the function value, right, or the height at the second point, right? So that's here. What is the height at my second value minus the height at the first value, which is right here, right? Divided by the x value at the second point, which is just, again, in this case, it was 1 plus h, right? And if I change that 1 to an a, then it just becomes an a plus h. And if I turn, right, so if I had just started at t equals a, and I go on to t equals a plus h, right, I've moved over h amount. And so what I want to do is I want to make that h value closer and closer and closer to 0, which is why we create a limit. So the final answer here, or the final formula, is you take s of a plus h minus s of a, right, the difference in the y's, and you divide by h plus a minus a. Now what happens is, right, h plus a minus a, my a's cancel, and so what I end up with is just divided by h, right? S of a plus h minus s of a is the limit as h approaches 0. And so we just want to be able to find that limit. And if you can find that limit, then you can find the instantaneous velocity at a particular point, right, at the point a, s of a. Okay, so here's the thing. Up until probably this class, we've only talked about slopes of lines, right? And what calculus is about is like the study of change. And the problem is most functions, unless you have a line, most functions have a rate of change or a slope that's changing, right? Because like I can look at, you know, the slope of this point, right, at the top, and it has a different slope or a different instantaneous velocity than like this point here, right? Because this one kind of has a slope that's like really negative. And then this point here has, I'm sorry, I'm having like technical difficulties. This point here has a slope that's like positive. And so basically what's happening is that my slope just keeps changing, right? So my slope at this point is steeper than here, and it's steeper than here, and it's steeper than here. And then when I reach a slope of 0, I actually start decreasing, and I have a negative slope here, and it starts getting more and more negative, right? It becomes steeper and steeper again. And so what you're finding is that your slope is not the same each time, right? Your slope is actually changing. And so this is the instantaneous velocity is finding the slope of any point, of a particular point on a graph. So the instantaneous velocity is actually the slope of the curve at a specific point. Because unless the curve is a line, that slope is going to change over time, right? And as does the velocity if we're talking about like the position of a particle or of a person or of a car. So yeah, and the average velocity is like taking 2 points, right, and finding the change in y over the change in x from those points, from A to B. So, okay, here are 2 examples. I'm using this function. S of t is negative 8x squared plus 10x plus 3. Go ahead and try to find the instantaneous velocity using the limits of s of t at t equals 1. And then do the same, but find an equation for just all of the instantaneous velocities on that function. So again, this is going to be with limits as well. Okay, so for the first problem, we want to find the instantaneous velocity using limits of s of t, which is the function that I defined up here. Okay, so side note, these are all supposed to be t's. because this is s of t. So, this is just kind of like a typo here. Or I guess you can make it s of x. And then we're good too, right? But it should be a function of whatever this thing is. So let's call it s of x. It's negative 8x squared plus 10x plus 3. So this is the function that we're working with, and we want to use that definition of instantaneous velocity that we have up here. So that's where I grabbed that formula from. So the limit is h approaches 0 of s of a plus h minus s of a over h. Okay? So in this case, right, we have the limit as h approaches 0, here's our equation, right, or a limit that we need to solve for the instantaneous velocity at t equals 1. Okay, so in this case, since our function is the one above here, negative 8t squared plus 10t plus 3, I'm going to write that down. All right, so here's our function s of t. And so in this case, a, right, or the x-coordinate that we're actually interested in finding the instantaneous velocity at is 1, okay, given in the problem. So we are going to plug 1 in for a in this limit first. Okay, so this is still just general form, right? I'm plugging 1 in for my a value. And so what I'm going to need to do is use the function that we actually have. So in this case, s of t is this function. So we need to find out what is s of 1 plus h. And so that's just taking this 1 plus h, like we do with functions, right, and plugging it in anywhere we see the independent variable in s of t. Okay, so here's plugging in 1 plus h for t. So keep in mind that you're going to have to simplify this. So 1 plus h squared, you're going to have to FOIL, multiply by negative 8, distribute the 10 into the 1 plus h, and combine like terms. Okay, so I'm going to go ahead and do that real quick. So here I'm just FOILing. 1 plus h squared is 1 plus 2h plus h squared. And then I distribute the 10, I get 10 plus 10h plus 3. Then I combine like terms. So when I combine like terms, right, I have to distribute this negative 8. And then, 10 plus 3 is 13, minus 8 is 5, okay? So once I get all that done, right, I'm simplifying this s of 1 plus h is all I've done, okay? Because that part we're going to need for the limit. And it doesn't matter where you simplify it, but you're going to have to simplify it somewhere. So this piece is equal to s of 1 plus h. So I'm going to change that. We also need to find what s of 1 is. Okay, so the only thing I need to do now is figure out what s of 1 is, right? Because that's this part here. So again, I go back to my original function, which is s of t, and I'm just plugging in 1 for t. So it should be negative 8 times 1 squared plus 10 times 1 plus 3, which should come out to be 5, right? I have negative 8 plus 10 plus 3, so that should be 5. So I'm going to replace s of 1 with 5. And then as I simplify, I should get negative h squared minus 6h plus 5 minus 5, so my 5's cancel. And I have negative h squared minus 6h divided by h, which I can simplify. So I pull out an h, so then I have h divided by h, which is just 1, so those cancel. And I'm left with the limit as h goes to 0 of negative h plus 6. And then we can just plug in 0 for h, and we get the limit is equal to just negative 6. So the instantaneous velocity of s of t at t equals 1 is negative 6. Okay? So number 2 is a little bit harder because it's not just with numbers. So I'm going to go ahead and do that, but not, I want you to try it, but the problem is usually, so up here we had t equals 1, so we had a specific time. This time we're just going to use t instead of 1, so we're going to use a variable. So we have multiple variables happening. So I'm going to go through that and show you what the answer is, but I'm not really going to spend time talking through the whole thing. So you should try it first to see, if you get stuck anywhere, see what's happening, and then check your answer and see if you did okay. Okay, so for this one, again, check your answer. If you got it right, don't listen to me. You can be done. Congratulations, you figured it out. If you didn't get it, you should probably just follow along for the next minute or two. So we started again with the limit as h approaches 0 this is like the thing that we started our notes with. But this time a is just a variable. It's just t. We don't know what time. Basically what we're trying to do is we're trying to find an equation of something that gives us the instantaneous velocity at any time of that particular function. So here's my s of t, negative 8t squared plus 10t plus 3. We already know that. That's given in the problem. And then s of t plus h, right? In the last problem, it was 1 plus h because I was looking at only one time, right, at t equals 1. Now I'm looking at t equals t, right, like at any time. So plug that in to the function. I get negative 8 times t plus h squared plus 10 times t plus h plus 3. So I FOIL the t plus h squared, distribute the 10 here, and then try to combine like terms, but it turns out there are no like terms, right? I've got a t squared, an ht, an h squared, a t, and an h, and then a 3, a constant. So those are not going to be able, you're not going to be able to combine those. So we're going to like go and change this thing, and hopefully you're recognizing this a little bit. We've talked about stuff like this called the difference quotient, potentially. And so hopefully you kind of recognize this. It's the same process that we did in class with the difference quotient. So this s of t plus h is this thing here that I've simplified. So I put that up there, and then I'm subtracting s of t, which is this thing here, right, the negative 8t squared plus 10t plus 3. And then, turns out the negative 8t squared, those cancel, the 10t and the 10t cancel, and the 3 and the 3 cancel, and I'm left with negative 16ht minus 8h squared plus 10h divided by h. And so if you cancel out the h's with the denominator, you get negative 16t minus 8h plus 10. And remember, we're taking the limit of this as h goes to 0. So that's this step here. I'm taking, remember, the whole thing, right? The instantaneous velocity is the limit as h goes to 0 of this thing. And so that would just end up being negative 16t plus 10. So what this does is, regardless of what time I'm curious about knowing the instantaneous velocity, it's actually giving me an equation to get the instantaneous velocity for that function. So if I said, what's the instantaneous velocity at t equals 0? You would plug in 0 for t here and say, oh, the instantaneous velocity is 10, which kind of makes sense, right? So at t equals 0, right, if I'm looking at my function, sorry, I've got a little lag time here, but at t equals 0, I'm right here. So we're actually looking at the slope of the line right here. And it's a pretty steep line, and it's positive, so our answer should be positive, and it is. So our velocity here is positive 10. And if I was like, oh, okay, what's the instantaneous velocity of the function at t equals 1.5? Again, just plug in 1.5 to this equation here. And that's it for today. I know that was a long lesson, but nice job. I wanted to just go through stuff and make sure you understood it. All right, bye-bye.